In this segment, we'll talk about how to solve a first order ordinary differential equation exactly. And we're going to take the case where we will be forced to take the next independent solution for the particular part. So you will come to know about it when we take the example. So here is the example which we are going to be solving. This is the differential equation given to us with the initial condition at 0 to be 5. Let's go ahead and see how we're going to go about solving it by using the so-called classical solution techniques, where we find the homogeneous part and the particular part. So your full solution becomes the addition of the homogeneous part and the particular part. Let's go ahead and concentrate on the homogeneous part first. So the homogeneous part can be found by writing the characteristic equation. So it will be 2 times m to the power 1, because it's the first derivative, plus 3 zeroth derivative, m to the power 0, equal to 0. So 2m plus 3 is equal to 0. So m is equal to minus 1.5. So that becomes the root of the characteristic equation, which allows us to say that, hey, the homogeneous part of the solution will be k e to the power minus x mx. So you get k e to the power minus 1.5x. So that is the homogeneous part of the solution. So in the next slide, we're going to concentrate on finding the particular part of the solution. Let's recall the differential equation which we had. It was as follows. And we just found out that the homogeneous part of the solution is k e to the power minus 1.5x. So let's see what the particular part of the solution is. The particular part of the solution is the form of the right-hand side, or the forcing function, and all its possible derivatives. Since the form of all the possible derivatives, e to the power ax, for example, is e to the power ax itself, the only term which we need to then consider is the term which is in the forcing function, which is e to the power minus 1.5x, so far as the form is concerned. So, but there's an issue here, because the particular part of the solution is same as the homogeneous part of the solution, or it's part of the homogeneous part of the solution. We cannot accept this as the particular part of the solution, because if we substitute this into our differential equation right here on the left side, we can get 0, and that won't allow us to find the value of a. So we have to look for the next independent solution. So we got to look at ax e to the power minus 1.5x as the particular part of the solution. So let's go ahead and see if we put that in our differential equation. So we're going to find the value of a by substituting the particular part in there. So we get 2 d by dx of ax e to the power 1 minus 5x plus 3 ax e to the power minus 1.5x. We're going to take the derivative of this function here, which is a product of two functions of x. So using that information, we'll get a e to the power minus 1.5x, because the derivative of x is 1, and then we'll get minus 1.5 ax e to the power minus 1.5x, because the derivative of e to the power minus 1.5x is minus 1.5 e to the power minus 1.5x. So we get plus 3a x e to the power minus 1.5x equal to e to the power minus 1.5x. So let's go and expand this and see what we get. You're going to find out this term is negative of that term, so that's going to cancel out. And that's going to allow us to say that, hey, this is the case. For this to be true for every value of x, 2a will be equal to 1, and that will imply a is equal to 1/2. So since a is 1/2, that means that the particular part of solution, which was of this form, is now 1/2 ax e to the power minus 1.5x, which is same as 0.5 ax e to the power minus 1.5x. So what we found out was the homogeneous part is k e to the power minus 1.5x, and we found the particular part to be 0.5x e to the power minus 1.5x. So the complete solution will be k e to the power minus 1.5x plus 0.5x e to the power minus 1.5x. And so the question arises that, hey, how do I find the value of k? You find the value of k by applying the initial condition, which is y sub 0 equal to 5. So 5 will be equal to the value of the y at x equal to 0. And that gives me 5 is equal to k. This part is 0, that's k. So k is equal to 5. So since k is equal to 5, the complete solution is 5 e to the power minus 1.5x plus 0.5x e to the power minus 1.5x, and that is the solution which you were looking for. And that's also the end of this segment.